Yay! Again, okay, so first order logic. What I want to do is start off by talking to you about the basic building blocks of this language. So the important thing here is to spoil a joke I'm going to make in about 2 slides. The key thing here is that FOL is more expressively powerful. It can say things and capture things that TFL couldn't. And that's because FOL has subsentential parts. The base unit of TFL was a sentence, right? Atomic sentences. The base unit for FOL is going to be a complex. It's going to be more like our actual model of an atom. It's going to have some electrons and a nucleus. It's going to have parts. So what we're going to do is talk about the building blocks, which is going to be a term and a predicate. And then we're going to get to the other really useful, in fact, the reason why we're interested in terms and predicates, part of this language, which are quantifiers. So we'll talk through this, and I expect going through this will take us through the bulk of our first part, right, up to the break. Then I want to pivot and talk about some particular forms of symbolizations into FOL. So getting used to some very simple ones, thinking about some paraphrase and some questions about quantifier scope. And then if we have time, we'll very quickly gesture at some issues about multiplace predicates and multiple quantifiers. So this is going to be the big task. I'd like to try and get through all of it, but importantly, it's really useful if we just get the beginning bits clear. The rest of it can come. We've got 3 more lectures to get through. So let's talk about the building blocks of FOL. So here's an argument, right? And it's a valid argument. I'll just tell you, I'm not going to bother asking. But if we symbolize this into TFL, we get something that's kind of problematic. Because if we symbolize this in TFL, we get something like this. And this argument isn't valid, right? Or better, to be strict, our premises do not tautologically entail our conclusion. So TFL doesn't let us capture, to go back a slide, this obviously valid argument. And that's bad. That's a limitation on TFL. It's not the end of the world. I mean, it was a tool designed for a specific purpose. It just happens that one tool can't do everything. This is the best we can do using TFL, thinking about this argument, which is problematic. And the issue here has to do with how the premises work. So the way we can actually capture this argument is by moving to FOL. So our first premise gives us a way to talk about Socrates in particular. We have a name for him, which will be little a in this case. And we can say of him that he has the property of being human. He satisfies the predicate is human. And then we can say, hey, everything, if it satisfies the human predicate, then it satisfies the mortal predicate. And then we can use a kind of modus ponens to get us to, well, since Socrates satisfies the H, he must satisfy the M. Therefore, A is an M. First order logic lets us capture the structure that TFL didn't. And the way it does it is by letting us split the atom. Instead of having just sentences, we have subsentential parts. And whenever you have a replacement for what used to be an atomic sentence, you're always going to have 2 subsentential parts. The core, you can see it here, is a predicate and a term. You can never have anything that's like an equivalent to a TFL atomic sentence unless you have a predicate plus a term. Might be more than one term if it's a multi-place predicate, but you always have to have a predicate and a term. So there's our new base unit. It's not just a capital letter anymore. It's always going to be a capital and a lowercase letter at minimum. So FOL as a language Right? Remember, TFL had basically 3 elements, 3 kinds of parts. FOL has 6. 2 of them are different kinds of terms, ways to let us talk about specific objects, or ways to let us basically range over objects. So we have names, and we have variables. We're going to talk about these one by one, but I think it's useful just to see everything right off the bat. As well as terms, we have predicates. Predicates we're going to express with capital letters. We can have subscripts if we want, same with these. And again, our base unit's always going to be predicate plus term. Then we're going to get the connectives. We get the same connectives from TFL. They work just like they did in TFL. We use them just like we did in TFL. They do the same things. Right? We have brackets. Hey, they do the same thing they did in TFL. Right? Same stuff, nothing new there. The big money, though, is the quantifiers. So we'll talk about these after we get through everything else. So connectives, we know how to do those. We did these. We know how to use the connectives. Brackets, well, we don't have to talk about those. But let's talk about names, variables, predicates, and then we'll get to our quantifiers. We'll go one by one. So as a run-up to the notion of a name, it's helpful to think about terms in English. In English, there's broadly 2 types of terms. There's singular terms and what we'll call general terms. Singular terms are words or phrases that are used to refer to specific entities. Nathan, Tilburg, California, the Netherlands. Every one of these, if it has a reference, refers to a single entity. A general term, however, picks out something like a type or a kind. Right? Dog, cat, student. Right? Again, the contrast here, take Mira, which picks out my dog, versus dog, which picks out the kind of thing that she is. And when we think about singular terms, which are used to refer to specific entities, there's broadly 2 types. There are proper names that pick out specific entities without describing them. Right? The fact that my dog's name is Mira doesn't tell you anything about her. In fact, you don't even know that she's a dog if you find out that Mira is her name. In fact, we've had many people listen to my wife and I talk about Mira, and they're like, oh, is that your daughter? Okay, in a sense. But contrast proper names with definite descriptions. Definite descriptions pick out a particular object in virtue of giving a description that one and only one thing satisfies. The tallest person in the room. Right? If that picks out anyone, if there is actually someone who's the tallest person in the room, right, it does so because they are the only individual who satisfies the description. Another example, Socrates versus the teacher of Plato. 2 different ways for us to pick out the same dead Greek dude. Now, this distinction helps us get a grip on 2 different ways of talking about things in the world. We can either talk about specific objects using singular terms, or we can talk about types, kinds of objects using general terms. Broadly and super roughly, names are going to be like this. They're singular terms. Variables are going to be like this. They're singular terms. Predicates are going to be ways for us to do something like general terms. So that's the run-up. Let's talk about the specifics. First element of our language are names. In FOL, names are expressed by lowercase letters a through r, with subscripts if we need them. What do? They function just like proper names, but importantly, unlike proper names in English, there's no ambiguity. Nobody shares names in FOL. Right? If Eric is a name in FOL, then there's only one person named Eric. Or another one, probably better, John. I met 4 people named John at the conference I was at over the weekend. Right? That could not happen in FOL. We'd have to have different names, first order logic names for them. There'd be John 1, John 2, John 3, John 4. Right? So there's no ambiguity with any FOL name. And importantly also, a name always picks out exactly one thing. And it always picks out exactly one thing. I'll say this now, I'm going to say this again later. We never have any empty names. If you have a name, it's guaranteed to pick something out. Now, notably, right, guaranteeing that names are never ambiguous and that names are never empty doesn't mean we can't have 2 names for one thing. So we could talk about Mira, we could talk about the dog owned by Nathan, right? Both of these would be something like names, right? Singular terms to pick out the very same object. So there's no problem with having 2 names for one thing, but we can never have one name for 2 things. And similarly, we could never have one name for nothing. Now, an FOL symbolization key, as you can expect, it's going to be more complicated than the symbolization key we had for TFL. First thing to note is that when we're looking at symbolizing with FOL, the key will tell us, hey, what things do the names pick out? Right? So A here names Socrates, little m names Mira, little n names Nathan. Right? Again, basic idea. Cool with names so far? Yes?
Why do we have to stop at R when we represent names?
Good. Because we need lowercase letters for variables. So variables are our other lowercase letter, and the R is a kind of arbitrary one. We just want to be able to distinguish between the ones that are always going to be names and the ones that are always going to be variables. That's a good question. So let's talk about variables. Grammatically, variables function very similar to names. We're going to express them with lowercase s through z, with subscripts if needed. But importantly, they don't do the same thing semantically as names do. Right? Remember, a name is always just a way for us to get to something, right? It picks something out. Well, a variable is a variable. Right? This should be ringing alarm bells for everyone here who took any maths class, right? If you did algebra, you had to deal with variables. Right? You had x squared, figure out, tell me what's the value of x. Right? A variable functions a bit like a pronoun. It's a way for us to indicate something like a gap and talk about the thing that we're going to plug in. Right? So I could say something like, okay, x loves y, but y does not love x. Fill in who you think of for x and who you think of for y. And by using the variables this way, we make it clear that you're supposed to plug in the same person for both x's and the same person for both y's. Another way again, right? You've come across this notion before if you've done a bunch of maths, or not even necessarily a bunch of maths, right? Every x is greater than 2 but less than 3. So this specifies a range of numbers already. And then what's this variable doing? It's saying, hey, plug in any number you want. It's going to have to be between 2 and 3. So again, what do variables do? They kind of stand in as pronouns. They stand in a way for us to label gaps. So grammatically, kind of similar to names. Semantically, fundamentally different than names. Names always take us to whatever it refers to. Variables, well, they're variables. We can replace them with stuff. Now, since they're variables, a symbolization key will never tell us what they refer to because they don't refer to anything, right? It stands for, if you like, every entity, or some entity, or no entity. Unlike, to go back a slide, these ones, which stand for specific, particular ones. Now again, the kind of important thing here is that we get this semantic difference. Names always take us to a referent. Variables, well, they're just a way for us to do some pronouncing. We need to have more stuff to kind of fill in. That's the basic first bit. Now, the third part is a predicate. And predicates are parts of language that we could broadly say ascribe properties. So, is in the logic class is a predicate. A dog slobbered on is a predicate. Is taller than Nathan is a predicate. Now, the thing to note with predicates is that they have gaps, right? ... is in the logic class isn't a sentence. You need to fill in the sentence's subject. You need to say, who is in the logic class? Similarly, a dog slobbered on ... isn't a sentence. You need to fill in who's the target, who got slobbered on. So predicates link up with singular terms to give us sentences. We take Socrates, we take the predicate as human, ram them together, we get a full sentence. Now, in FOL, we're going to express predicates with capital letters, subscripts if we need them. Right? And symbolization keys will tell us what each capital letter, what predicate it's expressing. So for example, I might have capital H as the predicate is human, capital T is woke up at 3:30 a.m., and capital T subscript 1 as is a terminator. Again, we can pick out any property you like, any basically adjective you like, and turn it into a predicate. So, as this already suggests, and I've said already, our basic unit is always going to be predicate plus term. The simplest one is going to be predicate plus name. That tells us that whatever the name refers to satisfies the predicate. So these are the three parts. Really, from this, everything else is going to stem. So this is what we got to get clear on first. So we can get a little grip on thinking about how to build FOL sentences by looking at how predicates and terms go together. So here's a sample symbolization key. We've got 3 names, and we've got 3 predicates. And I could write capital H little a to say Socrates is human. And I could say capital HX to say X is human. But note, X here isn't a name. This is just basically a way to say is human. I'm going to have to do some more work to fill in who the is. Right? And this is, again, to come back to the earlier question, one of the things you have to pay attention to is which letter is plugged in here. If it's a name, cool, we're done. If it's a variable, we're going to have to do a little bit more work. And similarly, using this key, I can write capital T little m for Mira woke up at 3:30. And if I wanted to write Mira woke up at 3:30 and Nathan woke up at 3:30, well, hey, we can use our conjunctions and our brackets. Right? So a lot of the stuff that we did before with TFL is going to keep on going. Just instead of having atomic sentences, our basic parts break down, right? They have predicates and terms. Okay. So, a way to kind of get a grip on this, let's do a few together, right? Here's a simple symbolization key. And here we'll go through some sentences. So, using this key, how would we do Mira woke up at 3:30? TM. So one thing, it's okay. No. In English, that would be the way we'd write it, right? We write subject and then the kind of predicate. But in TFL, predicate always comes first, right? So predicate and then whatever satisfies predicate. TM. Cool. Okay. This is the simplest kind of sentence we can get. This is basically the same as writing like capital A in TFL. How about Socrates is a terminator? T1A. Right. Dun, 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 dun. Right. Nice. So, okay, Socrates is a Terminator. No worries so far. Nathan and Socrates are human. HN conjunction HA, right? Because we can paraphrase this as Nathan is human and Socrates is human, right? Remember the stuff we did before with TFL? And then instead of just atoms, the atoms turn into parts, right? Predicate and term. So HN conjunction HA. HN tells us Nathan's a human. HA tells us Socrates is a human. Yes? That's not how our language works. So we have to have it written up like this. So basically, again, the way to think about it is this would have been like capital N for, say, Nathan is human, and this would have been capital S for Socrates is human. And we're looking inside what used to be our atomic sentences at the parts that make them up. That's the trick. So, okay. And our last one, right? If Mira woke up at 3:30, then Nathan woke up at 3:30. Yeah, TM conditional TN, right? If Mira woke up, then Nathan woke up, which is true. Okay. And again, note we could put the brackets on the outside for these sentences. Everything that we learned about symbolizing and paraphrasing for TFL comes back into play here, right? So all of the skills you've developed already still keep going. Okay. This is the core of it, right? It's going to keep getting more complex, but this is the core of it. Right? Every replacement for an atom, predicate, and term. Now note, in every case here, we've used singular terms, right? We've used names. We haven't used variables. And that's because, strictly speaking, a predicate plus a variable doesn't say enough yet. We have to know how to fill in the variable. And this is what quantifiers are going to do for us. So let's talk about quantifiers and domains, because this is how we're then going to figure out and know how to use the variables. Okay, so we have two quantifiers, the inverted A and the backwards E. The inverted A is our universal quantifier. First thing to note, you will never see a universal quantifier on its own. It's always immediately attached to some variable. That is the variable it controls. That is the variable associated with that particular quantifier. So upside down AX is basically a way for us to say for all X, or every X. Right? The variable is attached to the quantifier, and if it's the universal, it's saying everything can be substituted in for every occurrence of X. To use the terminology, every quantifier is always found next to a variable, and that variable is bound by that quantifier. So this says everything's an H, this says everything's a T, this says everything's an F. Again, the basic idea of the universal is that it's a function. It's a function. It's a function that tells us you can replace the X with every name and you're going to get a true sentence. So for all X, HX is equivalent basically to A is an H, and B is an H, and C is an H, and D is an H, and so on for every possible name. Similarly, we can have complex sentences. For all Y satisfies the sentence in the brackets. That tells us that if we plug in A for Y, we're going to get a true sentence. And if we plug in B for Y, we're going to get a true sentence. And C, and D, and for every name. The universal says, replace the associated variable with any name you like. You're guaranteed to get a true sentence. Okay. Yes?
If it's a complex sentence, then there are like two or more variables, right? So, what about for all x in that sentence?
We will come to that in 3 slides, I think. So importantly, the universal here tells us no matter who you plug in, it's going to satisfy the thing in the brackets. We then have to worry about, cool, what does the existential say? But we do the first thing first. We follow order of operations. This is the other reason why we start with TFL first. It teaches us to be really strict about following the order. Same thing here, it's just going to be a little more complex. Okay. So the universal, the upside down A, is the all. The existential, the backwards E. Right? Again, just like with the universal, you will never, ever, 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 ever see it on its own. It's always going to be right next to a variable. That's the variable bound to that quantifier. The existential is a way to say for some x. So this tells us there's something that's an H. This tells us there's something that's an F. This tells us there's something that's a T. There might be tons. It might turn out that everything is a T, or it might just be that there's only one. But there's at least something out there that's a T. So the function of the existential isn't to say that you can replace the associated variable with every name, but it's that there's at least one name that you can fill in to get a true sentence. So if we have existential x hx, it's telling us that either A is an H, or B is an H, or C is an H, or D, and you just go on for all the names. Similarly, for our more complex formula, it's telling us there's at least one name you can replace Y with that's going to give you a true complex sentence. Right? So it's important to get the difference between the two quantifiers. The universal, the upside down A, is an and, effectively. To go back a slide, right? It's an and. It says every name you fill in is going to give you a true sentence. This and this and this and this and this and this and this. Right? The existential is an or. This or this or this or this or this or this or this. And remember how we understand ands and ors. Right? And requires all of them to be true. All of them have to be true for the universal to be true. If there's even one that we can plug in that isn't an H, say, well, this universal is going to be false. In contrast, our existential is an or. Right? Either A is an H, or B is an H, or C is an H, or D is an H. So all we need is just one. If, somewhere in here, like M is an H, cool, then the existential's true. Because it just tells us there's something that's an H. Okay. So the important things to think about the grammar here, right, is again our base unit, predicate, and a term. If it's a predicate and a name, cool, you're done. If it's a predicate and a variable, then that variable needs to be associated with some quantifier, either a universal or an existential. Sorry, I know grammar's super fun. Everyone looks so like, it's okay, I understand. But honestly, once we get this thing tooled up, it's fucking magic. It does so much cool stuff. So, let's do some work. Let's see if we can do some symbolizing. Here's our key again. It's the same one as before. And let's introduce some symbolizing using the quantifiers as well. So suppose I wanted to say everyone's human. How would I say everyone is human? Yeah, I'm going to need my universal, right? For the everyone, universal. And if we have the quantifier, we have the universal quantifier, what has to come next? Or at least some variable, right? It could be a y, it could be a z, it could be an s. I don't really care. It needs to be some variable, right? So we can just use x to keep our lives easy. So universal x, right? And then what? hx, right? This is a way for us to say, hey, everything, right? You can replace x with any name you want, and it's going to make the h true. Or to put it in stricter terms, everything satisfies the predicate h. Everybody's human. Right? Okay. How about someone's human? Right, this one tells us everybody is. How would we say somebody is? Basically, we're going to keep the same broad grammar, but just instead of the universal, we switch to our existential. Right? Because all we need is just that there's someone who's human. Right? There's at least one. So our existential x, hx. Right? And note, we could have used y here, we could have used z, we could have used any one between s and z. It doesn't matter. All that matters is whatever one we write next to the existential, that's the one we write next to the h. Make sense so far? Cool, good, okay. How would I say there's a human and Mira woke up at 3:30? So, right, we want to say there's a human, which is basically the same as someone's a human. So existential x, hx. And then we use conjunction for our and we know how to do Mira woke up at 3:30. That's T, M. Ah. I think that's just because I was using an old one. This used to be for Yobka, but keep her in. So that should be TM. Typo there, sorry. Okay, good so far? We clear? So note already, we're seeing the quantifiers can interplay with our connectives. Now our last one. If Socrates is a terminator, then everyone is.
Conditional, universal, T1x.
Close. Yeah, we need to always, whenever you have the quantifier, it has to be immediately followed by a variable, right? Immediately. Right there, it's always right there, right? So, we know this is a conditional. Our antecedent's going to be Socrates is a terminator, T1A, and then our arrow, and then everyone's a terminator. For all x, T1x. Cool. Okay. Now again, don't stress. We've literally just started this, but we're starting to see how these things start to fit together, right? The connectives work just like they did before. Our symbolization schemes work just like they did before, right? So everything that we learned about when to use or when to use and, when to use the conditional, that still keeps going. Right? Just now, instead of having capital letters, we always have capital and lowercase. Those are the basic parts. And sometimes, if it's a particular lowercase letter, it needs to be governed by, controlled by some kind of quantifier. That's the general basic grammar. The trick is going to be the symbolization, the mapping from natural language sentences to FOL sentences. That's the hardest part of this bit. Because once you get this, once we are allowed to start talking about particular objects, predicates, and using quantifiers, right, that gain in expressive power, the grammar becomes much harder. Right? Again, just think about how difficult it was to learn grammar in natural language, right, versus how simple the grammar was in TFL. Right. Okay. So let's try a few more, and I want to use this one as a particular example. So if someone's a terminator, then everyone is. Using that symbolization key we had a second ago, well, we could write it like this. This tells us that if there's some x that's a terminator, then for every x, it's a terminator. This is perfectly fine. But there's a way that you might be tempted to write this that would be problematic. And that would be if we had this. If we kicked this quantifier up to the front. We wrote it like so. And the problem here is that we have what we call a clash of variables. Basically, right, we think about this x right here in the antecedent. We don't know who it's attached to, which quantifier is controlling it. Right? Is it the existential, or is it this universal up in front? The x's here are governed by both quantifiers, and that's a no-no. We cannot ever have that. Contrast that with the way we've written it up here. The scope of this quantifier is just the antecedent. The scope of this quantifier is just the consequent. But the scope of this quantifier is the whole sentence now. The brackets tell us that. So we cannot have clashes of variables. That we cannot have, because we don't know which function the variable is attached to. So what we need to do to fix this, well, what would we need to do to fix this? What could we do to fix this sentence? Wait, we could write it as the first sentence. What else could we do to fix it? How else could we make this work? Yeah, basically, let's just replace this x with a y. Right? As long as we keep different variables for our different quantifiers, we're fine. In fact, to put it another way, every quantifier should be attached to one and only one variable. Now, notably, you can use the same variable letter as long as the scope is different, but that's kind of a bad habit to get into. Right? Better to use different variables for different quantifiers. You don't have to, but it will make your life a little bit easier. Okay. One more little bit before we break, okay? It won't take 3 or 4 minutes. And the way to get into it is to think about beer, which is something I think about way too much. Well, actually, I don't think about it. I just make it go away. So, one of the things that did actually happen over the weekend was we were at a bar, and the bar ran out of beer. So the lady behind the bar told us, like, hey, all the beer is gone. And that was a tragedy, right? It was a genuine tragedy. But of course, it would have been a much bigger tragedy if what she meant was there's no more beer ever in the world. That would have been a genuine tragedy. I would have murdered at least one person. Right? So it's clear when she told me that there's no beer, right? Or that all the beer is gone, she didn't mean in the whole world. She meant more like there's no beer in the bar. There's no beer in our fridge. And actually, typically when we say this kind of thing, context serves to tell us what we're talking about. Everyone's human. Really? Well, this thing isn't human, right? And this should be in the range of our quantifier. We can call it Steve. Steve's not human. That means it's false that everyone's human. It's like, oh, you prick. I meant everyone who's in the logic class is human, right? Steve's not registered, though. He's just crashing. So the important idea here is basically that a lot of times we use context to tell us who we're talking about. But FOL doesn't allow for context to do this. Instead, we say, these are the things we're talking about. We're talking about the people who are registered for the logic class. Sorry, Steve. We're talking about the stuff that's in the fridge, of which none of it is beer. We're talking about everything in the world ever, right? Which, cool, there's lots of beer left, thank God, right? So more specifically, what we do when we're in FOL is we specify domains, right? A domain is a set of things that we're talking about. It's the collection of objects we're concerned with. Every FOL symbolization key should specify the domain. So the domain could be things in the fridge. The domain could be physical objects. The domain could be universal. That is basically everything that's ever existed and will ever exist. It could just be Steve. Right? Now, importantly, what quantifiers do is they range over this domain. That is, they serve as functions to pick stuff out. Right? The variables they bind, that the quantifiers bind, can be replaced by the things in the domain. Right? So a universal one doesn't necessarily say everything ever. It says everything in the domain. That's why to go back a slide, when the lady told me all the beer is gone, right, she could say something true despite the fact that the bar next door still had beer. The domain was restricted just to the stuff in her bar. Similarly, we could say everyone who's registered for the class, right, that's our domain. Then everyone's human will be true, barring some of you who might be Terminators. Right? So all basically says replace the associated variable with everything in the domain should still be true. The existential, right? It just says there's at least one thing in the domain you can replace the associated variable with. Something in the domain satisfies the sentence. Right? Okay. So again, domains we specify explicitly. Now, two things about domains, which are restrictions we are going to take as assumptions. The first is that we never have an empty domain. There always has to be at least one thing in the set of things we're talking about. Right? So the minimum domain could be just Steve, or just me, right? Or the number 2, or the letter A, right? But it can't be nothing. So no empty domains. And similarly, and we talked about this already, right? But is that every name that we're using has to pick out something in the domain. In the domain. Right? That is, we can never have an empty name. So if we introduce Steve as a name, it's got to pick out something in the domain if we're going to read it. We're going to make sense of it. Together, these help us do something really useful, which is that we can infer an existential from a claim featuring a name. That is, if we know that N is a T, we know that something is a T. But if we allow for empty names, then we can't do this, right? Santa wears a red suit, therefore something wears a red suit. Wait, shit, is Santa real? No. Right? Sorry to destroy some dreams, right? So the important thing here is that a domain must have at least one member, and a name must pick out exactly one member of the domain. But a member of the domain may be picked out by one, many, or no names. This is going to come back again later, right? You might have a domain of one thing and have every name refer to that one thing. Or you might have some sentences that just don't have any names, in which case, cool. You don't have a name for the thing in the domain. Okay. All of this we'll talk more through as we get through some symbolization practice, which is what we're going to do after the break. So why don't we take, it's 35, it's 36 now. So why don't we come back at 45 in 10 minutes? Okay? 10 minutes and we'll come back.